Welcome to video 3, 11.3 combinations. So today we're going to talk about when order does not matter. Okay, so this first example, 5 people who were made iconic by death were Marilyn Monroe, James Dean, Jim Morrison, Janis Joplin, and Jimi Hendrix. Imagine you ask your friends, of these 5 people, which 3 would you select to be included in a documentary featuring the best of their work? You're not asking your friends to rank their 3 favorite artists in any kind of order. They should merely select the 3 to be included in the documentary. We are interested in which artists are named, not the order which they are named for the documentary. So the order, I don't care who's first in the documentary, second or third. I just want these 3 to show up. So we're getting into a combination. Okay, so a combination of items occurs when the items are selected from the same group, the 5 stars. No item is used more than once, so I only can use one of the 3 people, okay? One of the 5 named, right? So Jimi Hendrix is a guitar god, but your 3 selections cannot all be Jimi Hendrix, all right? They have to be distinct. The order of these items makes no difference. I could see Morrison, Joplin, Hendrix is the same group as Hendrix, Joplin, Morrison. So long as they're included, okay? So just remember, permutations are what we talked about in last video, and those are problems involve situations in which order does matter. But combinations are problems that involve situations in which order makes no difference. Order does not matter. So let's take a look at these examples down below and determine if we have a permutation or a combination, okay? So for each of these guys, we're going to determine whether the problem involves permutation or combination. So this first one, how many ways can you select 6 free DVDs from a list of 200 DVDs? So you have to think, does it matter the order in which I select these, or is it just asking me to choose 6? Hopefully you recognize that order doesn't matter here. This is a combination, okay? I just care about getting those 6 DVDs. I don't care the order in which I get them. So let's look at the second example. In a race in which there are 50 runners and no ties, in how many ways can the first 3 finishers come in? So think about it. Does order matter? And in this case, it does. It does matter because there's a first place, there's a second place, and there's a third place. So this is a permutation, okay, where the order matters. I can't have a different first place than a second place. They're distinct, okay? They're distinct. So now we're going to get into some problems that involve combinations using our formula. So similar to permutations, we have a formula for combinations. So note this notation there. NCR means the number of combinations of n things taken r at a time. We can develop a formula for NCR by comparing permutations and combinations. Consider the letters A, B, C, and D. The number of permutations of these 4 letters taken 3 at a time is, let's turn to the next page. 4, because there's A, B, C, D, with the permutation for choose, and I have 3 letters in my words, essentially, that we're talking about. So from last video, we have 4 factorial over 4 minus 3 factorial, which gives us 24. You can see the 24 different permutations here. Okay, where order matters. But if we're just talking about combinations of these letters, let's see what we can come up with. So hopefully we recognize, well, one combination between our letters of A, B, C, and D would simply be A, B, C. Then I could have A, B, and D in any order. Then I could have A, C, D in any order. And what's the last combination? Can you see what we're missing? We're missing a B, C, D. So when we're talking about combinations, we've really only got 4 different combinations. Because the order of items makes no difference, so I can mix these letters up, I can mix these letters up, but they still all count as the same combination. So each row of 6 permutations represents one combination. So these are A, B, C, just in different orders, but that's a combination of those 3 letters. This second row is a combination of A, B, D, okay? But it's in any order. This third row is a combination of A, C, D in any order. And this fourth row is a combination of B, C, D. So there's a total of 4 combinations. Thus where we use the notation 4 choose 3, 4 C3. And that equals 4. So what's the formula? Okay, there are 6 or 3 factorial times as many permutations as there are combinations. So let's take a look. This is how they kind of lead us to our formula here, where the important piece is this last portion here. So to figure out the combination formula, the number of possible combinations of n things taken r at a time is NCR, which is n factorial over n minus r factorial times r factorial. So highlight this guy. Right? This is our important formula right there, that next dealing with combinations when order doesn't matter. So let's look at this first example here. You volunteer to pet sit for your friend who has 7 different animals. How many pet combinations are possible if you take 3 of the 7 pets? So I don't care the order in which I take those pets for a walk. I'm just taking 3 randomly. So that's our 7 pets total, but we're choosing 3 to take for a walk. So using that formula, we have 7 factorial over 7 minus 3 factorial times 3 factorial. And now we're just going to simplify, okay? So 7 factorial over 4 factorial. Well, this is like saying 7 times 6 times 5 times 4 factorial over 4 factorial. So those cancel. Writing 3 factorial out, I just have 3 times 2 times 1. So what we should note here is 3 times 2 times 1 is the same as 6. So those guys cancel, and we're left with 7 times 5, which is 35 combinations. Okay, I want you to try checkpoint 3 on your own. How many different 4-card hands can be dealt from a deck that has 16 different cards? So get your setup. Set up your factorials, your formulas, simplify, and see what you get. Okay, hopefully you got the same as me. So we said 16, choose 4, because I have a deck of 16 cards, but I only want 4 cards in my hand. So we have 16 factorial over 16 minus 4 factorial, which is 12 factorial, times 4 factorial. And then when we clean it up, the 12 factorials will cancel, and I'm left with 16 times 15 times 14 times 13 over the 4 factorial, 4 times 3 times 2 times 1. So cleaning that up, we could go ahead and say, we can go ahead and say 14 and 2, that's going to go to 7. 16 over 4, that's going to go to 4. All right, and then 15 over 3, that's just going to go to 5. So we have 4 times 5 times 7 times 13 for a grand total of 1,820 different combinations. This last example is a little bit different because it deals with 2 different combinations. So let's suppose a zoo has 6 male bears and 7 female bears. 2 male bears and 3 female bears will be selected for an animal exchange program with another zoo. How many 5-bear collections are possible? So what we need to do is we need to make a combination for the males, and we need to make a combination for the females. And then we're going to use that counting principle to multiply those guys together. So the males, we have 6 to choose from, but we're only choosing 2. So 6 choose 2. And here's our setup for our combination. For the females, we have 7 bears to choose from, but we're only choosing 3. So here's our setup there. When we simplify the males, we get 15 different combinations for the males and 35 combinations for the females. Multiplying those two together, we get 525 possible collections of a 5-bear outcome. If you have questions, come to class and we'll discuss.